That's why if you ever lick a 9-volt battery, it kind of hurts because it has a higher current. But if you touch a 9-volt battery on the top, it doesn't hurt because there's different resistances.
Tanner, tech, Tanner, tech, Tanner, Tanner, tech, Tanner, tech, Tanner. Hello, this is Tanner Tech.
So, voltage, like I was saying yesterday, is this type of is this unit of measuring the electricity. And it's the difference between electrons on one point, on this wire, and electrons on this wire. The negative wire will have a lot more electrons than the positive wire, which will just have a few electrons. Now, electric current flows the opposite way electrons flow, because electrons want to get to this part by going through a wire this way, in this direction, but electric current flows the opposite way through this direction. That's voltage, the difference between two parts of different electric potential. Now, current, on the other hand, is how many electrons are flowing through one point in a certain amount of time. So, if the electrons were flowing through here to here, the current was flowing this way. If there were a certain amount of electrons passing through this point at any one given moment, that's how much current is flowing. And we also learned about Ohm's law, and that's a super, super important part of electronics. It is E equals IR, or voltage equals current times resistance. So we know that by this, if resistance depends on the voltage and current, and the current flowing through a circuit depends on the circuit's actual resistance. So if a circuit has more resistance, then less current flows. If a circuit has less resistance, then more current flows. Hey Max, what's up?
Hey Tanner. Sorry I'm late.
That's fine. Oh.
I'll find a seat, don't worry.
Okay.
Don't let me interrupt.
So, what happens is, that is pretty much voltage and current right now. Yesterday we also learned about diodes, and I promised I'd bring a vacuum tube. So this is a vacuum tube, like I was talking about, that has the heater inside it, and it has the two plates, the one hot plate and the one cold plate. You can pass this tube around. Now the cool thing about tubes is that they were invented about over 100 years ago. So that tube right there is 60 years old, which is pretty cool. And this tube has a diode inside it, or a vacuum tube diode, where there's two plates, and the current can only flow from one plate to the other because one plate has a cloud of electrons around it that flow to the other plate. And so it only lets the current flow in one direction. And that's kind of like the modern day diodes that we have that only allow current to flow in one direction in the circuit. And the diodes, remember from yesterday, none of these markers out of the way. The diodes look like this in their circuit design. So the current is only allowed to flow from this direction through the diode in this way. If the current tries to flow the opposite way, then it gets stopped up by this diode right here. Now I also brought diodes, so I brought a whole bunch of other electronic components, and so I'll pass around a few diodes for you guys to look at. Okay, so just pass these things around. These are two separate diodes. Now, the diodes I'm passing around, there's two different sizes of diodes. Now, diodes can have different properties about them. Like, some diodes will only allow a certain reverse voltage. That means, you know how I said if there was a voltage across this side and this side, it would be stopped, there would be no current that's flowing? Well, if the voltage gets too high, then it'll break down the material inside the diode, and the voltage will start flowing back through the diode. And that's the reverse bias. So the big diode that you see right there has an extremely high reverse bias. It's about 4,000 volts. And that diode right there is actually used in microwave ovens to produce the high voltage that makes the microwave work. So the tiny diode that I'm passing around, that one can only has a reverse bias voltage of about 50 volts. That means if the voltage right here exceeds 50 volts, it'll explode. So that is pretty much diodes. Diodes are pretty self-explanatory. Well, no. Diodes are pretty simple because they're kind of like a one-way switch. It's kind of like a one-way valve that only lets water flow through one way, but stops the water when it tries to go the other way. Yesterday we also learned about transistors. Now transistors, like I was saying, are kind of like light switches. They only allow the transistor to turn on when there's a voltage across the base. Now, the transistor, and I'll pass one of those around too. The circuit diagram symbol looks like this. Now, when I say circuit diagram symbols, I'm talking about the symbols that electrical engineers use to show how a circuit works. Let me show you an example of a circuit diagram. Okay, the circuit diagrams are made up of a bunch of these symbols that show exactly how a circuit works. And here's one for example. So this is a circuit for a power amplifier. Now, this may look like gibberish to you at first. It may just look like a weird maze out of science fiction. But this is actually telling an electrical engineer, or whoever's building a circuit, how exactly that circuit needs to be built. It's kind of like blueprints for a house. And this is cool because there's thousands, millions of circuit diagrams, and you can use those to recreate almost any electronic device. This one, for instance, goes to an amplifier. And as we can see, like that little symbol I drew up there, there's these transistors inside the amplifier. And there's actually quite a lot of them. One right here, one here, one here, one here. And these transistors not only act like switches, but they act like amplifiers to amplify the current that's going in. Like let's say we had a voltage going into this transistor, and it was a sine wave. I always pick the wrong marker. And the voltage going in was a tiny sine wave, and it had a voltage of about 0.5 volts. Then if we had a special circuit on the output, like this circuit right here, then we will get an extremely large voltage on the output of this. That voltage would be however much the transistor has of gain. So if this one was 0.5 and the transistor had a gain of 10, then this sine wave that would be coming out of the transistor would have a voltage of 5. Because if the gain of this transistor is 10, then the output voltage will be 10 times the input voltage, which is 5 and then 5 volts. So in this diagram, we can see a lot of different components, and this has most of the major components of electronics. So here we see resistors. Now I know up here I was drawing resistors, like this little squiggly line that looks like this, but resistors can be drawn in many different ways, just like this little blue line right here. And so each of these little blue lines are resistors. And so you can see how important those resistors are inside electrical circuits, because they're used almost everywhere. Then we have transistors, which I will get into explaining. Now there's two types of transistors. There's NPN transistors, and there's PNP transistors. Now, NPN transistors have a base, they have an emitter, and they have a collector. Now you can think of this in the literal sense of the words, where the collector collects the current from the top, and the emitter emits the current from the bottom. So if you turn on the base and you have a switch, then you'll have to have the current flowing from positive, which is up here, and let's say that's 5 volts. And you want to put a resistor on that voltage, because if the voltage exceeds a certain current flow through the transistor, you'll blow out the base. So we'll have to put a big resistor on there that goes to the base. So that slows down the current going into the base, so that way it's not too high. Now when this current flows through the base, it'll flow through the base, out the emitter, and to ground, which is negative. And when that current starts flowing, then a proportional amount of current, proportional to the gain of the transistor, is going to be allowed to flow from another positive source through a circuit, through the collector, and back through the emitter to ground. And this circuit can be a motor, it can be a light bulb, it could be a speaker, it could be anything. And this circuit will be allowed to turn on if you allow current to flow through the base. And even if it's just a tiny amount of current flowing through the base, it'll allow a large amount of current to flow through the collector to the emitter of the transistor. And so that's pretty much how the most basic of the basic NPN transistors work. Now we also have another kind of transistor called a PNP. Now PNP transistors are kind of tricky, and I don't really like them that much. But you gotta learn them, because it's a vital part of electronics. So a PNP transistor has an arrow up here. And if you look at the screen, we can see that we have an NPN transistor right here, because the arrow is pointing out of the bottom. And we have a PNP transistor right here, because the arrow is pointing into the top. Now a PNP transistor will allow the current to flow through this part of the transistor if current flows from the base to ground. Because this is kind of funky. So if we put a resistor from here to ground, and this is a circuit diagram symbol for ground, it'll allow current to flow from here through the arrow to here. So the current in this circuit will actually need to be switched, because we can't put the actual circuit that's going to be drawing the current out here. We'll have to put it down here, which means that the current will flow through the collector through the base into ground. That will turn on the transistor, allowing current to flow through the collector, through the emitter, and back to ground, through whatever circuit you want to run it inside. And so that is how a PNP transistor works. Now there's thousands of different kinds of transistors, and there's different transistors that have different voltages, and different gains, and different other characteristics. So I'm going to pass around two transistors right here. And now transistors come in all different kinds of sizes. Some transistors are even as big as my hand, and those are huge transistors that can sink power supplies or power things that are up to thousands of watts. Like remember I was talking to you about watts and how much heat different amounts of wattages dissipate? Some transistors are able to sink so many watts, and those transistors are really cool. But some transistors are so tiny, they're smaller than a human hair. They're almost microscopic. And those transistors are the kind of transistors that are inside your computer. And those transistors are called metal oxide field effect transistors, or MOSFETs. And I'll explain that in just a second. I just need to get some new markers, because these ones aren't very good. So if you just hold on for a second, I'm going to go to Mr. Wolney's classroom and see if he has any extra expo markers. Sorry about the delay. Mr. Wolney had tons of expo markers. Okay, so now we're going to talk about field effect transistors. Field effect transistors are pretty cool because they, instead of working on a current that flows through them, they work on an electric field across them. So we have the field effect transistor, and it looks something like this. It's this line with three dashed lines on this side, and then on this side, the lines go from here to here and down here, and they go from here to here up to here. Then we have the gate. Now, the terms of a MOSFET are different than the terms of a transistor. On a transistor, we had base, collector, emitter. Now, on a field effect transistor, we have different terms. We have a gate, we have a drain, and we have a source. So the gate is right here. It is similar to the base of the transistor. We then have a drain, which is similar to the emitter. We have a source, which is similar to the collector. So in this MOSFET, if we have a voltage between the gate and the source on the bottom, then it'll allow current to flow through the drain, through the MOSFET, and down to the source. Now the cool thing about MOSFETs is even after you take the voltage off the gate, then the transistor will still be on, because there's something called capacitance between the gate and the source. Now, forgive me for not talking about capacitors yet, because those are one of the most important aspects of electronics. And once you learn about capacitors, you'll kind of understand how computers work with these MOSFETs inside. So capacitors, the circuit symbol looks like this. Now if you look inside here, you can see there's lots of capacitors. There's one right here, one right here, one right here, one right here. And these capacitors are kind of like little batteries that hold energy for a certain amount of energy. So some capacitors are huge and they can hold large amounts of energy, and some capacitors are small, so small, they can hardly hold any. Now, capacitors work by having two plates. Now, some of the plates of the capacitors are huge and some of them are tiny, but pretty much what happens is the amount of electricity a capacitor can hold is based on how big the plate is, the surface area of one side of the plate. And I'll draw something like this, and how far the plates are away from each other. So in this example, we have two plates, and both plates have a relatively large surface area, and they're relatively close to each other right here. Now, if we apply a voltage across each plate, so one plate would be charged to like 10 volts, 1 volt, one plate would be ground, then it would cause a quick current to flow through this capacitor, and that current would eventually stop, and each plate would be charged to a certain amount. That means one plate would have a few lots of electrons on it. One plate would not. And so that way, even if you take off the power source, then the plates are still going to be charged to a certain voltage they were given. Now, that means that this stored energy can be used for something else. But capacitors are also cool because they have something called AC impedance. Now I was talking about resistors and how they use Ohm's law. So when you put a DC current through them, they resist. They stop the current from flowing. Well, capacitors have something called AC impedance, and it's kind of like DC resistance. So if you put a DC signal across a capacitor, the DC would charge the capacitor and cause electrons to go on each side and a quick current to flow. And then after that, the capacitor would be charged, and no more DC current would be able to pass the capacitor. With AC current, since the plates are constantly switching from positive to negative and negative to positive, then the current is always going to be allowed to flow between the capacitor. So if you have a capacitor that is a bigger capacitor, then it's going to take longer to charge. So if this current flows through and it's not fully charged and then it switches direction and tries to flow the other way, that means not as much current is going to be able to flow. But if the capacitor is really small and it charges really fast, and so the AC signal, which goes like this, charges the capacitor, and the capacitor is fully charged by the time the AC signal reaches a voltage, that means the rest of this voltage is not even going to be used. And then when it goes down, the same thing is going to happen. So if you have different sizes of capacitor, then it'll cause different amounts of electricity to come out of the wall. And so these capacitors are sometimes used in AC power supplies to change the amount of voltage that is coming from the wall. And those are actually widely used in those CFL light bulbs. You know the little spiral ones that you screw into the ceiling? Those ones, their circuits are based on capacitors to change the high voltage from the wall to a little bit lower voltage to run the light bulb inside. So, capacitors are pretty cool, and I'm going to show you a demonstration of capacitors in the form of this capacitor bank. And through this demonstration, you'll see how these capacitors work and kind of how some other circuit elements work. So first off, I'm going to draw my circuit for this capacitor bank box. Now, I was passing around some capacitors. Well, I'm going to pass some capacitors around right now. And you can see that they're varying different sizes. And there are two types of capacitors. There's electrolytic capacitors, and there are film or ceramic capacitors. Now, electrolytic capacitors have a bigger storage because they have something inside called an electrolyte. And they also have lots of surface area on the plates. If you ever cut open one of these capacitors, you'll see the plate just spiraled like this. So it has tons of storage of electricity. Now, ceramic capacitors are just two little plates close together inside a ceramic shell. Now inside my power supply that I have right here, the capacitors are electrolytic capacitors, which means they can hold a lot. Now capacitors are measured in farads. Now a farad is a lot. 1 farad capacitor would be a super capacitor. So most capacitors are in the microfarad range. A microfarad is like this. Now if you look at those capacitors that I'm passing around, actually the smaller, oh, see this one? If you look closely at this capacitor, you can see on it that it has capacitance on it. It says 100 UF, like that. So that means it can store 100 microfarads of electric charge inside it. And some of the other capacitors you're passing around have other ones. Like that small green one that you just passed right there, that capacitor I think has 100 nanofarads, which is even smaller than the electrolytic capacitor. And these small capacitors can be used for transmitting an audio, like in this amplifier, to block out DC voltages, which will make your audio sound all weird. They put capacitors. So it blocks the DC like I was saying, but it lets the AC pass. It's pretty cool. So now, back to my power supply that I was talking about before. So this power supply uses a transformer, transistors, resistors, and capacitors, which are all parts we've learned about. So I'm going to draw the schematic for this up here, so you guys can kind of know how it works. So to start off, we have a power supply of 12 volts coming from that power supply back there. This power supply will come over here to the center of a transformer. Now transformers, remember how I was saying they have a certain amount of turns in each side, and if there's bigger turns on one side, then it'll make the voltage coming out bigger. Well, what happens is we have this transformer, and we have all these windings on the secondary side. Now on the primary side, remember how I was saying DC voltages, that current flows only in one direction? Doesn't work with the transformer, because it will just make it a magnet. And that magnetic field can't be made to make this other side have a stronger magnetic field. So we need to make something that turns this DC current into an AC current that's constantly flowing through this transformer, so we can get it to a higher voltage to make these capacitors work. Now, how this works is two separate transistors. So I'm going to just draw these real quick right here. Just a second. Okay, so both of these transistors are now grounded. So that means if we apply a voltage to the base of one of these transistors, then it's going to allow the current to flow from positive through this coil of the transistor, of the transformer, through the transistor and back to ground. Now the current can flow in two directions depending on which transformer is activated. And so we want to activate the transistors one at a time. We want this transistor to activate first, which means that the current will flow this side, and it will make the magnetic field going through the transformer go through this direction. And then we want this transistor to activate, making the current flow through this way, making the electricity in the transistor flow this direction. Now, how we do this is we're going to use the other transistors to connect to this one. So I'm going to connect this transistor up to here, and this transistor all the way down to, here, through resistors on each side, of course, to limit the current so the transistors don't explode. Anyway, it uses two transistors to create a higher voltage on this side of the transformer. Now this voltage is AC, and AC voltage can't be actually used to charge these capacitors. So we have to turn that into DC current. And to turn it into DC current, we'll use a diode. Because remember, the diode only allows the current to flow in one direction. And so it will stop all the current that's flowing through the other way. So that means that when the current flows to the transformer this way, and allow it to come through here and charge the capacitor right here. But when the current flows the other way, it can't charge the capacitor. So that means these capacitors will charge pretty quickly. Now, one capacitor isn't enough for me. So I went ahead and I added about 20 capacitors, all in parallel. Now, parallel makes more capacitance. If you had a capacitor right here that was 10 microfarads, you had a capacitor right here that was 20 microfarads. Now, how much capacitance do you think would be total between these two capacitors? What?
30.
Yep, 30. 30 microfarads between these two capacitors, because you're doubling their holding energy, because you're putting two of them together. That's like taking two water bottles and putting them together, they can hold twice the water. Now, if we put capacitors in this way, where we put them in series, which means we connect the top of one to the bottom of the other like this, and each one was 10 microfarads, we'd have a different story right here. Because these capacitors would have different amounts of capacitance. They wouldn't change in the same way these capacitors would. This total capacitor right here would only have 5 microfarads, half of the capacitance between these two. Now the reason behind that is because you're increasing the plate area between this, and so it's going to decrease the capacitance. And so now back to my circuit. We know that we have a bunch of capacitors that are able to be charged at a high voltage, and this makes about 400 volts to charge this capacitor. And now, a lot of electronics can be used for fun. This is one of them. So I'm going to turn this on. Turn this on. And you can see my little voltage dial is rising. Now, what's going to happen now is I'm going to short out this power through a piece of solder. And you'll be able to see exactly how much capacitance and how much power is inside the circuit, because the solder will explode. So just be ready for that, because it's kind of loud. It's kind of bright. Okay, so it's charged. And so I'm going to touch these two wires to the pieces of solder. Now brace yourselves, because it's kind of loud.
Sounds like a hobbit.
Yeah, but a lot louder. So that kind of shows you what these capacitors can do, because they're able to discharge all of their current. Now, a normal AA batteries, like a normal battery that you would buy in the store, those batteries can only discharge a little bit of current at the same time. That's because these batteries have a series resistor inside them that is formed by the chemical reactions inside their plates. The batteries that you would buy at Walmart, or the AA batteries that you use in your mouses and your calculators and your clocks, those batteries have this series resistor inside them. So the circuit diagram for a battery looks something like this. So we have a big line followed by a small line, followed by a big line, by a small line, by a big line. Now, in a normal circuit, a battery looks like this. But if we think of a battery theoretically, then it will have a little resistor right here. And that means these batteries can only discharge a certain amount of current at one time. So they wouldn't be able to power something that draws a lot of current, because it has this little hole in the end, like a resistor, that only allows a little bit of electrons to come out of the battery. So it can't put out that much electric current. But capacitors, on the other hand, don't have this theoretical resistor. So they can discharge all the current they want. Now, some things don't draw that much current. The light bulbs in our ceiling, since they're 60 watts, they only draw half an amp of current. Now, half an amp is pretty small. Now, okay, I'm just trying to think if there's any components that we missed. Oh yeah, inductors. So inductors are these little electromagnets that I was telling you about before. Sorry, I kept grabbing the wrong marker. Now, inductors are these little electromagnets that look something like this in a circuit diagram. Now, what happens is the electricity flows through this inductor. The current flows through, and it creates this rising electromagnetic field around the inductor. Now, this electromagnetic field can be stored as energy because, like I said in a transformer, an electromagnetic field can be used to create power on the other side. So if we put a lot of current through this inductor, which is pretty much just a coil of wire, and it can be a coil of wire around something that's empty, like just air, or it can be a coil of wire around a little piece of metal. Either way, it'll make a magnetic field. And once you stop this current flowing through it, that magnetic field will be released through this inductor. And that can create an extremely high voltage coming out of it. That's kind of how switch mode power supplies work. Now, switch mode power supplies are the ones that you find inside your computer, inside inverters, inside almost anything that needs to create a different voltage. Now, I was telling Braden before about switch mode power supplies and on a bike and how those can reduce and increase electricity levels. So a switch mode power supply pretty much utilizes this concept of this inductor that has a magnetic field. And so I'll pull up a quick picture of a switch mode power supply circuit so I can kind of understand, help you understand. Okay, so this is like a super complicated switch mode power supply circuit. We're not going to learn that today. That's not a lot of stuff to learn. But this is a simple one. What happens is there's power here, and if you turn this on, then power is allowed to flow through this circuit, through this inductor, and back through load to ground. And that charges up the magnetic field. Now what happens is when you turn off this transistor, that magnetic field is able to go through this diode and through this capacitor to charge it to a higher voltage that is able to make this so it has super high voltage across this capacitor. That's able to run this. So if I were to put 6 volts in here and have a circuit that turns this on and off, then we would be able to get any voltage out of this side from 0 to 500 volts. Now, in Braden's example, where he wants to have a bike that converts 12 to 6 volts relatively efficiently, we have to have another type of switch mode power supply. And can't seem to find a circuit for on right here. That is a switch mode power supply that I just showed you that increases the voltage a lot. There's some switch mode power supplies that decrease the voltage. Let me see if I can find one that does that. Okay, here we go. Here's what I wanted to show you. This is how Braden's example would work. So what happens is this circuit would switch on this transistor many times per section. And what would happen is the current would flow through this inductor, creating a magnetic field. Now what would happen is this circuit is a little bit harder to explain than the other one, but that would allow the current to flow through the capacitor this way, discharging it. So pretty much what the circuit is doing, which is kind of hard to explain, is it's reducing the voltage, but keeping the wattage the same. Now with resistors in a circuit that would lower the voltage, it is reducing the voltage, but that reduced voltage is getting lost to heat. But in this switch mode power supply circuit that are used in computer power supplies and in Braden's bike charger example, it's going to super efficiently reduce the voltage that's coming out. And it's kind of hard to explain this circuit. But anyway, that is how Braden's example works. Any other questions right now? I think I've gone through most of the electronic circuits. We've gone through the transistors, and the MOSFETs, and the inductors, the resistors, electric current, electric capacitance. Now, if there's anything you don't know, or that I'm not teaching well enough, just Don't be afraid to ask, because I'll be glad to help you. Now, okay, so you may be wondering why I have a camera back there, and pretty much I have a YouTube channel that makes videos about electronics and how the different electronics work. Now, I have like a few thousand subscribers, and some of my videos have quite a lot of views. But I was just thinking I could put this class on my YouTube channel so other people in the world can see. I also have video release forms because, according to the office, I'm not allowed to post a video without people's consent. So, I mean, I'm just gonna post the video, and it's pretty much just focused on me the entire class. But if you guys want to, then you can sign that, so I will be able to post this video on YouTube, so more people around the world that don't have access to my class can learn how electronics work, and they can learn how different things work, because I think it's super important to teach people about electronics. So I was just thinking videoing this class would be an awesome way to help people. But anyway, just sign that and get it back, and that's just giving me permission to post the video on YouTube. But anyway, this video right here is something that I posted, and it's pretty cool. It utilizes a circuit to make a fidget spinner spin super fast. Now, I noticed one of you guys had a fidget spinner yesterday, but most people, when they spin those little fidget spinners, they spin them pretty slow. But I built a circuit that is able to make these fidget spinners spin super, super fast. And it's pretty cool. I'll show you the first part of this video. As you can see, that fidget spinner is spinning about 1400 RPM. Now, that's just another thing electronics can do. Now, because I have this knowledge of electronics, I was able to just create a circuit that allows you to make a fidget spinner spin super fast. I'm going to show you this circuit right here, and I'm going to explain kind of how it works, because I think the best way to learn electronics, after you basically understand the different components, is to look at different circuits and see how they work, because that really helps you understand how the electronics interact with each other and make them work in a circuit. So in my fidget spinner circuit, I have a MOSFET, a metal oxide field effect transistor. And that MOSFET helps make this circuit use the large amount of current that it does. Now, I have this electromagnet or inductor inside my circuit. Now, this inductor creates a magnetic field, and this magnetic field attracts my fidget spinner. So that fidget spinner has a magnet on each little leg of it. And pretty much what happens is, whenever this spinner comes near this magnet, then there will be this other switch right here, which is called a magnetic reed switch. So when this magnet passes this reed switch, then it will turn it on, and then it will make, and it has this little two things inside right here. And these two little things that click a little tiny switch. Now, the switch can't really turn on too much current, so it needs to go through this MOSFET transistor. So what happens is, when the magnet passes this switch, it'll cause current to flow from positive right here. I know I'm drawing my circuit diagram symbols in some weird area, but it'll cause the current to flow from positive into the base of this MOSFET every time this magnet passes here. Now, when that happens, it'll allow the current to flow through this inductor from positive voltage, through this transistor, and back to ground, which turns this inductor on and causes it to push the magnet of this spinner away. And so every time the spinner spins and the magnet attracts this switch to turn on, it'll cause this thing to push it away, and it'll keep it spinning faster and faster. Now, I was telling you about that capacitance inside a MOSFET that makes it stay on afterwards. And so you need to put a little resistor on the end of this MOSFET from the gate to ground to discharge that capacitance inside the resistor, so the MOSFET doesn't always stay on and burn up the edges. So that's one circuit that I built. It's pretty cool to understand. Now, we're going to talk about manufacturing circuit boards. Now, manufacturing circuit boards is done using a soldering iron. And I have two of these soldering irons with me today. And these are a little bit difficult to learn kind of how to solder, but it's really important. Like I was saying on this circuit, soldering is the way to connect metal circuit components together to make a circuit that is able to function correctly. And so soldering kind of takes a little bit of time to learn how. But I was thinking that you guys could come up here and practice soldering and test it out to see how it works. Let me just discharge this. So you guys can come up here after these soldering irons have warmed up and test out soldering and try it out. Now these things take a little bit of time to warm up. They're pretty fun to use, and I'll have you solder some wires together, and I'll teach you guys how this soldering works. Because soldering is the most basic skill of electronics, and it is useful for almost anything, anybody who wants to build anything. Now tomorrow we're going to do projects. I'm going to bring in some stuff to do projects, that way we can do stuff. I'll bring in some circuit board manufacturing materials, and I'll have each of you guys design your own circuit board for something that you want to do. You can design these circuit boards using just Sharpies. Sorry I didn't set this up before class.
Do you want me to pass this around? Or
Oh no, not yet.
oh, okay, you just threw it. Okay.
I was just okay. So this, before I go into soldering and stuff, Braden told me yesterday he wanted me to talk about this Peltier chip. It's the thing that goes super cold or super hot. Now, it's pretty cool. You guys can come up and feel it if you want. But this thing gets hot or cold depending on the voltage that is going through each side. So, I connect this to the power or not. And if you feel this side, you can go over it. Now, put your hands on both sides. Feel it. I'm going to turn it on. No, just like this. Yeah.
Okay.
It's really hot. So if anyone else wants to feel the Peltier chip can come up. I'll explain how that works. So the Peltier chip is formed using two different plates. Now these plates have these little tiny little nodes on each side underneath it. You can. One side will get hot. See my one, like, yeah. Just wait for it to cool because it's kind of hot. Well, anyway, it has these little nodes on each side. And these little nodes, if you apply a voltage to each of them, then it's kind of hard to explain, but it's able to actually move the heat from this side to this side. So it's not actually, well, the way it's making it cold is it's moving all the heat from the cold side to the hot side. So that's why one side gets super hot while one side gets super cold. But these Peltier chips are pretty useful for cooling large electronic devices and other things. Now I think these soldering irons are warmed up, so if you guys want to come up here, I can teach you a little bit about soldering. There we go, they're warmed up. Okay, so you guys can come up here, and I'm going to grab some wire. Now, just all of you can come up here, and you'll have to probably take turns with these soldering irons. But you can come up here and grab them. So pretty much what I'll have you guys do first is put some solder on some resistors. So take it and hold it kind of like a pencil in your writing hand. And then you can pretty much just touch it to a piece of metal. And then after you touch it to a piece of metal, then you put some solder on it, and then put solder on that metal. So you can try soldering these little resistors together. And I'll cut up some wire so that way you guys can solder some wire. So I gave you a big piece of solder and you can use this piece of solder. So try soldering together these resistors. See how they're twisted together? Now try putting some solder on the resistor like that. Now what you have to do when you're soldering is you can't just touch the soldering iron to the piece of metal like that. You have to touch it and let it heat up, and then touch the other side to the soldering iron to let solder roll into it. So if you touch that to the side and let it heat up, then you touch the soldering iron here. See how there's molten metal on there now? And if you try to untwist those two resistors, you can't untwist them anymore because there's solder on it. And so you just solder together those two pieces of wire. It's pretty cool. Let's say I was to have my resistance be 630,000 ohms. Now, in order to get this recommended amperage to kill me, we can figure out how much volts we're going to need to do that. And so, to calculate that, we're going to use Ohm's law. E equals IR. You can see how that's super important. And so, our E, or voltage, is unknown. And so we'll multiply the current that can kill somebody by this resistance right here. Now remember that when my hands were dry, they had this resistance. When my hands were wet, they had a resistance way lower than that. I kind of forgot what it was. But that resistance can be calculated to figure out the recommended voltage that is lethal. Now that doesn't mean that all voltages are going to kill you, because some voltages, even if they have amperages way lower than this, will still hurt. Like one time I touched this capacitor bank, and it didn't feel good. But if we calculate this, that's 0.015 times 63,000. That means the recommended voltage that would probably kill me if I had that means the voltage that would kill me if I had my fingers dry like that would be 9,000 volts to get that current flowing through my body. But if it was wet, it would be far less than that. It would be really far down, almost close to 100 volts. So you can see that voltage doesn't always mean that you will get electrocuted, because people's skin can have varying different resistances based on like where their skin is being subjected to the electrical charge and where that charge is happening. Now that doesn't mean that you should go touching these ports, because this is 110 volts AC and that is dangerous. Electricity has an inherent danger behind it, but if you're able to understand the electricity and know how to use it, know when to touch different ports and when to not touch different things, and you'll be able to learn how to not get hurt by electricity. Now, I've learned from experience, kind of, about getting hurt by electricity. I've been shocked by a great many amount of devices, but eventually I learned that some things you can't touch and some things you can. And I haven't gotten shocked in like 6 months. But electricity is pretty cool, but it does have a danger. So whenever you want to build an electric something, then you always need to make sure to learn about it and have common sense while you're building something. So that way you don't get hurt or you don't. Yes, okay. See you later, Braden.
See ya. Thank you, Tanner.
You're welcome. Anyone have any questions about the safety and the current that kills people and stuff? No? Okay. Well, that's why these two cords right now have a potential difference of 12 volts, and if I touch them, I'm fine. But if I were to put these on my tongue, that would hurt, and it would potentially make a current that could kill me for that. Because my tongue, since it's wet, it has a extremely low resistance, and so it can let a larger current flow through. That's why if you ever lick a 9-volt battery, it kind of hurts because it has a higher current. But if you touch a 9-volt battery in the top, it doesn't hurt because there's different resistances. That wasn't me. That must have been the ghost in the classroom. Oh, right. Okay, let me fix this real quick. Okay, so next we're going to be talking about microcontrollers. Okay, there we go. Finally drew my Arduino. But this is pretty much something you can program to have different outputs on different pins. So let's say I want to turn an LED on and off once every second. Now, you could build an electronic circuit to achieve this purpose, but there are other ways you could do this. Or if you wanted to make a robot so it drove forward, then turned, and then drove forward again, you could use a microcontroller. So a microcontroller has input pins and it has output pins. And it has this thing that allows you to be able to control it from a USB, so you program it from a USB. Now what happens is you give it this code to use to execute, and I'll show you some code on my computer. And I'll actually show you a microcontroller right here. So it's pretty cool because depending on what your code says, it'll turn different pins on to 5 volts or 0 volts at whatever time periods you want, or in response to other stimuli. Like, you could have a pin that has music in, and your Arduino could measure that frequency of the music, and then use that to do something else. Now that 555 timer chip that I passed around isn't a microcontroller, but it is a similar size to the AT-Tiny microcontroller. And the AT-Tiny microcontroller is this small, but it can have this input and output stimulus. So I'll show you a picture of Arduino, and I'll show you some code, because microcontrollers are a super important part of electronics, because they allow you to control other things that maybe would take an entire huge circuit to do. You can do it with a tiny little controller. So this is a picture of an Arduino Uno. And as you can see right here, it has a USB port, and these pins right here go to different parts of the board. And so up here are the input and output pins. And so these pins can be turned on or off based on what code you put on here. And I'll probably bring one of these in tomorrow, because I know someone was talking about wanting to make a robot car. Usually takes a little bit to load. But this is pretty cool, and it's how I used my entire Christmas light system for Christmas, when I controlled all my Christmas lights to a certain song. So I'll open up my sketch about the Christmas lights, and I'll show you kind of how this code works. So these things just say the different pins of your Arduino and what they do. And then down here you can turn different pins on, which is high, or off, which is low. And depending on how you turn these pins on or off, you can have your Arduino do so many cool things. Like you could have it turn on lights over here, or turn off lights here. It's pretty cool. And I'll probably bring one tomorrow and explain it more in detail that way. So back to that 555 timer that I was showing you before. Now 555 timers are awesome circuits, I think. Even though it's this little tiny circuit, it can do so many cool things. Oh, yeah, you got it a little bit stuck there. That's fine. So do I. So this little 555 timer that I was saying has this big circuit inside. But it can also do a lot of cool things. Like if you ever want to make like a little sound, like a tone, then you can use a 555 timer to actually make this little piano. You can also use a 555 timer to blink a light at a certain pitch. You can use a 555 timer to turn on a light when you press a button once. You can use a 555 timer for pretty much anything. I'll pull up I put the 555 timer circuit on the intro. And I'll kind of show you how a 555 timer is able to work and how you're able to use an integrated circuit. Because even though an integrated circuit is this complete circuit that's housed inside this little tiny plastic casing, it still needs external circuit components in order for it to work. Because if you just tried to hook up a 555 timer to power, it wouldn't do anything. So if we look at a 555 timer circuits, then we can see kind of how it's able to work. So the reason I'm teaching 555 timers right now is because I think they're an important part to electronics, because they can be used for a lot of things. So here we have ground, we have VCC. That means that's the places where you put power, because the current in the 555 timer circuit, in order to make all the circuits inside here work, is going to need to be powered by the current flowing from positive through the circuit and back to ground. Alright. So you connect that to a battery, to your power supply, to anything else you want to do. Now, these other ones right here are able to make the 555 timer do other things. This circuit right here, this pin, turns on the 555 timer circuit. So it is able to actually run. And then if you apply different voltages to different pins, and you put resistors and capacitors between trigger and discharge,